Hello again, guys. Just before I go into a little more detail about the black body radiation spectrum, I just thought we would do a little bit of light revision. Now, as you probably remember from your physics lessons, the speed of light is approximately 300 million meters per second. So let's see how that relates to wavelength and frequency. Now imagine you had a frequency of, let's say, 1 cycle per second. Okay, so there's 1 cycle per second. So in this diagram down here, we can see that this is 1 cycle. It's 1 cycle. So if we say that this is 1 cycle per second, this one wavelength must take 1 second. And if we know that the speed of light is 300 meters per second, that means at a frequency of 1 cycle per second, or at a frequency of 1 hertz, the wavelength from here to here must be 300 million meters. So let's just write that up here. Wavelength, there it is, 300 times 10 to the power of 6 meters. Okay, so that was simple enough. Let's try another one. Okay, in this example, let's say the wavelength is 1 meter. The wavelength is 1 meter, which happens to be about the wavelength of a radio wave. So therefore we're saying that the length of one wave here is 1 meter. Now if light travels at 300 million meters per second, and we know that this length here is 1 meter, it must mean that there are going to be 300 million of these 1 meter cycles per second. So the frequency is going to be 300 million per second. 300 times 10 to the 6. Okay, therefore, with a wavelength of 1 meter, the frequency is 300 million per second. So now I want to introduce a new unit, and this new unit is the wave number. It's a unit which climatologists like to use. And all wave number is the number of waves which occur in 1 centimeter. So, okay, I've drawn a centimeter here. It's not to scale, of course, but if we were to imagine how many waves we could fit in this centimeter. For example, let's just do a little experiment here. 1, 2, 3, 4. So this green line here would have a wave number of 4 cycles, or waves, yes, per centimeter. Another way of writing that is centimeters to the minus 1. Therefore, in this example, if one wavelength is 1 meter, then in 1 centimeter there would only be 0.01 waves. So the wave number would be 0.01 cycles per centimeter. Okay, let's do another example. Let's say we had an example of a wave number of 1 cycle per centimeter. 1 cycle, or 1 wavelength per centimeter. Well, that's quite simple. If we have 1 cycle per centimeter, then we must have a wavelength of 1 centimeter. Let's have a look at the diagram. here's one wavelength, that's one cycle, and therefore the one cycle must be 1 centimeter. And of course 1 centimeter is 0.01 meters. Okay, I hope that's sort of clear to you. So basically all wave number is the number of cycles there are in 1 centimeter. So from the wavelength we can calculate the frequency. If we have the wavelength or the frequency, we can calculate the wave number. But can you also remember that I said if we know the frequency, we can calculate the energy. So let's have a quick look at that now. So you can probably remember that I explained that the higher the frequency, the higher the energy. And I explained that because I said if there was a higher energy difference between the energy shells when the electron falls back to its original shell, a photon is given off, and that photon is equal to the difference between the different energies of the shells. So up here we have the formula which we can use to calculate the energy of a photon compared with its frequency. So the energy equals Planck's constant, which is like a number we can just take off the internet or out of a physics book, multiplied by the frequency. So let's go back to our example and have a go at doing that. Okay, just clear away some of this stuff. So to calculate the energy per photon, the formula E for energy equals H, which is Planck's constant, times V, which was the frequency. So let's say in this example, if we had a frequency of 1, that's 1 wavelength per second. Let me just move this up here. So if we look up Planck's constant in electron volts, it comes to 4.1 times 10 to the minus 15, which is an incredibly small number. So we said the frequency was 1 wavelength per second, so 1 multiplied by Planck's constant, 4.1 times 10 to the minus 15. Yeah? The energy level of one photon would equal, in fact, yes, 4.1 times 10 to the minus 15 electron volts. So let's just write it here, 4.1 times 10 to the minus 15 electron volts. Okay, so from this, I hope you can all see that wavelength, frequency, wave number, and energy, they are all related to each other. Okay, see you next lesson. Bye.